finally, now that we're done with this module, let's just summarize what we've learned in this module, because it was quite a bit. In the hypothesis test for a population mean module, we looked at the 4 steps of a hypothesis test as they relate to a claim about population mean. The first step was to determine the hypotheses, the null and the alternative. The hypotheses are claims about the population mean mu, first of all. Second of all, the null hypothesis is a hypothesis that the mean equals a specific value, mu sub 0. Usually we say current mu is the same as old mu in a lot of our examples, but sometimes it's not that case. The alternative hypothesis is a competing statement that mu is less than, greater than, or just simply not equal to mu sub 0. So the alternative hypothesis looks like mu is less than mu sub 0. In other words, the actual mu is less than the original mu, or the opposite, that the actual mu is greater than the original mu or the claimed mu. Then the test is one-tailed. When the null hypothesis is just that the two are not equal, mu does not equal the old mu. I don't know if it's bigger, I don't know if it's smaller, but they're not equal. Then the test is two-tailed. I want to know the area beneath the curve on the left and the right. In the case of a matched pair design, the variable is the difference in 2 measurements, and mu is the mean of the difference in the population. We saw that in this module. Second step would be collect data. Since the hypothesis test is based on probability, random selection or assignment is essential in data production. Additionally, we need to check whether the t-model is a good fit for the sampling distribution of sample means. To use the t-model, the variable must be normally distributed in the population, or the sample size must be more than 30. In practice, it is often impossible to verify that the variable is normally distributed in the population. If this is the case and the sample size is no more than 30, researchers often use the t-model if the sample is not strongly skewed and it doesn't have a lot of outliers, or if it has no outliers. Okay, then our third step is going to be assess the evidence. If a t-model is appropriate, determine the t-statistic for the data sample mean. The t-statistic, here's the formula. If you haven't written it down, that's a good idea. It's the sample mean minus the population mean in the numerator divided by the estimated standard error, which is S, the standard deviation of the sample over the square root of n, the square root of the sample size. Use this test statistic together with the alternative hypothesis to determine the p-value. The p-value is the probability of finding a random sample with a mean at least as extreme as our sample mean, assuming that the null hypothesis is true. Also, remembering that the applets are going to ask you for degrees of freedom, that's n minus 1, the sample size minus 1. In all hypothesis tests, if the alternative hypothesis is greater than, the p-value is the area to the right, because on the x-axis, the greater values are on the right of the test statistic. If the alternative hypothesis is less than, those are the values on the left of the x-axis, the p-value is the area to the left of the test statistic. If the alternative hypothesis is not equal to, the p-value is equal to double the tail area beyond the test statistic. So you could find the area on the right and double it, or the area on the left and double it. It should be symmetric, so it shouldn't matter. The fourth step, the last step, would be give your conclusion. The conclusion is the logic of the hypothesis test is always the same. To use a conclusion about h sub 0, we compare the p-value to the significance level alpha. Alpha is often 5%, but sometimes they specify it to be larger or smaller than that. If the p-value is less than or equal to alpha, we have enough evidence to reject h sub 0. The null hypothesis, we can conclude that there is significant evidence in favor of the alternative hypothesis. On the other hand, if the p-value is greater than alpha, we fail to reject the null hypothesis. We conclude the sample does not provide significant evidence in favor of the alternative hypothesis. We write the conclusion in the context of the research question. Our conclusion is usually a statement about the alternative hypothesis, that we accept alternative hypothesis or we fail to accept it, and should include the p-value. So those that are kind of statistics savvy know exactly how sure we were here. Now let's see a few other notes about hypothesis testing. Okay. Remember that the p-value is the probability of seeing a sample mean at least as extreme as the one from the data if the null hypothesis is true. We're assuming it's true, innocent until proven guilty. The probability is about the random sample. It's not a chance statement about the null or alternative hypothesis. Hypothesis tests are based on probability, so there's always a chance that the data has led us to make an error. If our test result is rejecting a null hypothesis that is actually true, that's called a type 1 error. If our test result is failing to reject a null hypothesis that is actually false, it's a type 2 error. If rejecting a null hypothesis would be very expensive or controversial or dangerous, then we really want to avoid a type 1 error. In this case, we would set a strict significance level, alpha really small, like 0.01 or something. Finally, remember the phrase garbage in, garbage out. If the data collection methods are poor, like you're not doing a random sample or the sample size is way too small, something like that, then the results of the hypothesis test are meaningless.